Welcome back. Let's continue from where we left the last time. That was about the growth potential of civil aviation. Of course, this was before the COVID-19 outbreak occurred. Not long ago, only 6 months ago, it was on no one's agenda, and we, except a few, I should also add. Civil aviation report was uploading a growth of more than 4%. So let's start from where we left the last time with the idea of civil aviation growing more than 4%. Let's get started. Okay, in civil aviation, speeding up of production is going to be crucial. Airbus, in a forecast published in 2017, predicted that air traffic will grow at 4.4% a year over the next 2 decades. Let me read this again to digest it a little. More than 4% a year over the next 2 decades actually accounts to double and no less, requiring, according to Airbus report, some 36,000 new passenger and 830 cargo aircraft at a total value of $5.8 trillion. We have a chart about this that we are going to have a look in a moment. Boeing's forecasts are, if anything, more bullish. They are expecting a 4.7% annual growth in traffic and more than 41,000 new aircraft and a total value of $6.1 trillion. So obviously Airbus and Boeing are hoping to get a large chunk of this about $6 trillion in the coming years. How about the graph? In 2018, we see the global aircraft fleet of the world is about 20,000 aircraft. Now, which aircraft are counted? Passenger aircraft with more than 100 seats and freighter aircraft, cargo, above 10 tons. Okay, so according to that criteria, we are talking about 20,000. You see the 1,000 here? 20,000 aircraft today. And in 20 years' time, that would be 2037. You will be my age then, probably. What we see is the doubling of the fleet, the global fleet. The share of Asia Pacific is increasing. A larger part of this is due to China, of course, but not only to China, but to the Far East, Southeast Asia, etc. North America, Europe are also expanding. Middle East expanding as well. Latin America. So Asia Pacific is definitely growing above the trend. So how are we going to sustain that growth? To meet such demand, both firms will need to up their game, and they are doing so. A consultancy, Oliver Wyman, said in a report last year that it expected production of Airbus's A320, this is the workhorse, the most common aircraft of Airbus, and Boeing 737 each, to jump from around 40 a month to 60 a month. Those figures may need to be adjusted a bit after the 737 accidents, but that's the trend. Okay, so air traffic is going to grow about 4%. It's our take from the two paragraphs. So this is about manufacturing, and the techniques of manufacturing are definitely going to change to increase efficiency. So these companies are already working very efficiently, and still they have to double their capacity, and this is not just going to increase the factory size, etc. So the scale up has a lot to do with efficiency, we understand. So therefore the techniques we must be talking about. In the next paragraph we look at the techniques. Okay, let's have a look at the techniques. Techniques like using looms to improve the manufacture of parts. Remember, looms are to be used for laying the composite structures in the resins we discussed earlier. But other plants are also a food, meaning that are also coming. According to Grazia Vittadini, Airbus's Chief Technology Officer, the key to the future is connectivity. Now, before putting emphasis on connectivity, I would like to suggest to have a look at Grazia Vittadini, the person who is the Chief Technology Officer of Airbus. Airbus is the European manufacturer, which is the closest one to us. Think of yourself going to work for this company and have a look at what this person is in her mind, and it is a she. If you have a look at this person's CV, you will see that she graduated from aeronautical engineering from Italy, and she is specialized in aerodynamics. But please take time and study her CV. Now, coming to the connectivity part. What is connectivity? Connectivity is about things talking to one another. Internet of Things. Internet of Things. IoT. We have all heard about this. Therefore, it would be easy to dismiss that as a buzzword invented by the marketing department. But there are all those sensors aboard every 350. 350 is a marvel of technology, and this thing has many sensors. We know that there are computers of different sizes and capacities on an airplane, but also think about the sensors that are collecting physical data to be processed by the computers. So how much data are we talking about? We are talking about nothing less than 30 gigabytes of data. These sensors transmit every day, and similar, if not quite so abundant, quantities of data from other types of Airbus aircraft. So similar amounts of data we are talking about, tens of gigabytes, are the basis of a system called, now this is a trademark, Skywise, that allows both the firm and its customers to track what is going on across entire fleets of aircraft. The customers of Airbus company are of course airline companies like Turkish Airlines, Lufthansa, etc. So all these companies will be investigating, mining this data for trends. And eventually this connectivity idea will lead to every plane having an electronic twin on the ground. Now again, I would like to repeat the point of me reading this article is to show you how we can really benefit by reading this type of high quality reports of currency. I mean that they are current, only 6 months. So this is really the frontier of aircraft manufacturing, technology, and business. This is why my point is not to pass you some information, but to show you this is the highest quality of reporting. And I want you to see how beneficial that is to understand this really, really high level ideas. Coming back to connectivity, this will lead to every plane having an electronic twin on the ground. This system is already established for jet engines. Manufacturers create a computer model of each engine they make. A computer model means software, a program. So a digital twin of a jet engine is a software that is running parallel with the real jet engine, and then through the sensors update parameters of the jet engine during or after every flight using the data collected by the sensors, as I am telling you. That way, the electronic simulacrum, the simulation, the program, the second self or the twin of the jet engine can keep an eye on its physical counterpart, flagging up potential problems and predicting better than an arbitrary maintenance schedule. An arbitrary maintenance schedule is you check components every 2 weeks, for example, or after every flight, when parts needs replacing. An arbitrary maintenance schedule when parts need replacing. What works for engines can easily be extended to the entire aircraft. So this is already happening with the engines, and it is going to be extended to the entire aircraft, and even to a time before an individual plane is born, tracking its components as they are put together. So in other words, we are now talking about the logistics following that up even before the plane is born. This is like tracking your cargo coming from Hepsi Burada, for example. This way, the process of assembly can be monitored, integrated, and speeded up. And we know that it must be speeded up. It must speed up, and it must do so reliably. Think of the 737 MAX tragedies. So, next, aside from the manufacturing line, we also have a paragraph talking about the carbon fiber reinforced plastics. This is somewhat further into the future, not really very close yet, but plans for new generations of aircraft are already being laid. There is talk, for example, of carbon fiber reinforced plastics having a serious makeover. What's wrong with them? Let's see. The resins currently used to bind the sheets and tapes of fiber together are what are known as thermosetting plastics. Once baked in the oven, these hold their shape forever. So they are not plastic in the real sense of the word. Most of the materials that a layman would think of on hearing the word plastic, though, are different from this. They are thermoplastics. Normal plastics, most of them are thermoplastics. This is why you see people on the streets looking for them, because they can be recycled. But the resins used in the carbon fiber reinforced polymer business are not. They cannot be softened by heating and then remolded again. They behave, in other words, like metals. And like metals, they can in the future, the manufacturing business are trying to make thermoplastics of those resins so that they can be softened by heating and then remolded in an indefinite number of times. So people are trying to make, the main idea is that people are trying to make carbon fiber reinforced plastics really recyclable by using thermoplastics. And in this way, they will be like metals. They could be riveted as well, so they can be recycled, which saves money and burnishes a firm's green credentials, green, environmentally friendly. So we are talking about recycling here, and the issue is about really sustainability. So I would like you to think about the current CFRPs are not fully recyclable. Therefore, the businesses based on them is not fully sustainable. But this is definitely not an issue of the near future, as the paragraph suggested at the beginning. And here is something really radical. Looking even further ahead, Airbus is now experimenting with spider silk, produced on an industrial scale by genetically modified microorganisms. Now, this is what we call multidisciplinary research. Suddenly, we are talking about biotechnology. Spider silk, you want to produce it on an industrial scale. How do you do that? By genetically modified microorganisms. Definitely, this is the remit of molecular biology and genetics. So it looks like a molecular biologist, a geneticist, is going to create a lot of value, if not in the near future, but certainly will, for making aircraft components. This is really an interesting point. Such silk, spider silk, is stronger, tougher, and lighter than almost any man-made material. It's really hard to understand this. How can an organic the resins are organic, and carbon is an organic carbon-based molecules are organic, but this is more than that. This is not organic chemistry. This is really biology. The chemistry of, I like to say van der Waals bonds. Such silk is stronger, tougher, and lighter than almost any man-made material. And more than that, it's hard to put these things together. We are talking about aerospace engineering, the frontiers, the future of flight, and at the same time talking about spider silk, trying to produce it in an industrial scale by genetically modifying microbes. This is truly exciting. Work on it is still at an experimental stage, but it is not a dream. But Airbus is collaborating with MSilk, a German biotechnology firm, to develop silk reinforced polymers. Now, in your next interview, just mention spider silk reinforced polymers. that might one day become substitutes for carbon fiber reinforced polymers. This is truly exciting, natural fabrics. On my presentation, I have a link for this company, a short video of what they are doing. They've actually made a lot of progress, exciting progress. Okay. Now, let's come back to the larger picture. As to the design of airframes, cautious improvement rather than radical change is the order of the day. Now remember, this is the thesis of this whole report. Cautious improvement, a tinge of conservatism rather than radical change. Radical change, innovation, invention is the order of today. So cautious improvement. This is a good way of thinking about the improvement in airframe technology. No one has forgotten the lesson of the Sonic Cruiser. We have a picture of the Sonic Cruiser in our presentation. It's here. So this is the Sonic Cruiser 2000. Have you ever flown in one? No, no one has ever, because this wasn't built at all. Why it wasn't? A simple answer, very quick and short, brief, simple, oversimplified answer is because it was too radical to be built in many different senses. I suppose it's more radical than the Concorde itself. So this airplane was never built because it was too radical for everybody. And also the fuel consumption, as we will just see in a moment, was not on par with the other solutions. Though the design for that unbuilt aircraft retained a cylindrical fuselage that looks the same for passengers to sit in, it had delta wings, aft means at the back, and a pair of canards at the front for stability. Those small wings at the front. It would, as the name suggests, have cruised at Mach 0.98, just below the speed of sound. It bombed, didn't work. No one wanted it, mainly because its fuel consumption would have been too high. Most passengers seemed to prefer cheap tickets than speedy arrival. There was also a problem with its awkward shape. Awkward shape, this is to put it very bluntly, which would have made it difficult to fit into existing infrastructure of global airports. Well, it seems some conservatism is at hand. Nobody is prepared to change the airport infrastructure for a plane or build a complete new airport for this awkward looking aircraft. It takes some boldness to say it's an awkward shape. It is a different shape, nevertheless. That doesn't mean, I hope you are also enjoying this high quality reportmanship, if I might say that. I'm really happy that I am actually reading something that is coming from the frontiers of aerospace manufacturing technology. That doesn't mean that the design of airframes and wings in particular cannot be improved. In January 2019, Boeing announced it was working on a proposal that will change the look of an aircraft quite a lot if it is implemented. The transonic truss-braced wing, as the firm calls it. I will show a picture of this. There is one in our presentation. Will have a pair of wings fixed above the fuselage, each supported by a brace that is fixed below the fuselage. This arrangement allows the main wings to be both thin, saving weight overall, and long, which reduces drag. Remember, higher this ratio, the higher the lift. The upshot is the eternal desideratum of better fuel economy. So this is better fuel economy. Let me show you what it looks like. This is the transonic thrust braced wing, TTBW. See, the wings are much thinner, incredibly thin really, and you can make them longer, so they have less structural stress on them. I find that this is unbelievably thin, really unbelievably thin. I would bet my money on this. The plane looks awkward again, and even ugly this time. But it looks like money is the king, so who knows? Let's see, but I will put my money on this design. So that is Boeing. And then on the Airbus side, I have I think this is so I have a link over there for you to check. Coming back, that was Boeing. And what's happening on the Airbus side? Well, Airbus is working on BLADE. It's a nice acronym. Breakthrough Laminar Wings. Breakthrough Laminar Wings. Laminar Aircraft Demonstrator. That is mouthful. BLADE is making smooth wings. An experimental wing design that is being test flown this year, 2019. BLADE is an attempt to create a wing that has no irregularities, even small ones, to disrupt the smooth flow of air over its surface. This too is intended to reduce drag. BLADE wings have no joints and therefore no rivets or fasteners. Have smooth, glossy surfaces like a mirror really. They may also be fitted with flaps that deflect insects during takeoff and landing. And let's have a look at it once again. So this is the BLADE wing due to Airbus. I have a nice video from an engineer from this team, is the lead engineer, I guess, explaining the technology and the promise of this mirror-like shiny wings. Okay, let's conclude the manufacturing article by discussing the promise of Delta wings. It's a dream, not going away yet, as the article says. In theory, the optimum shape for an aircraft that relies on fixed wings to provide its lift is such a delta, with wings and body blended together so that the whole structure provides lift. Designs for such vehicles pop up from time to time and might make effective freighters, cargo planes. Whether passengers would like them, though, is moot, uncertain, and probably not. Most seats will be a long way from a window, and evacuation in an emergency might be hard. So it concludes, don't expect them soon. So this concludes our discussion of the manufacturing. I would like to go back to the presentation file to recap what we have discussed. We talked about connectivity and digital twins. This is already done for most of the jet engines, and it's coming to the whole airplanes, aircraft. We learned that sensors on board A350 transmit about 30 gigabytes of data every day. So generation of data from many sensors helps assess the integrity of the whole structure and its components. Next, we talked about the promise of biotechnology instead of the use of spider silk, maybe not in the near future. And a German company is actually furthering this research and manufacturing. So I have a YouTube from that company that will tell you more. This is it's interesting that molecular biology and genetics is going to add a lot of value, or have the promise, have the potential to add such value to aerospace technology. I would like to highlight that. And then coming back to our discussion on conservatism and innovation, here is a Boeing program that is going to create extremely thin wings by means of a truss structure. And then we discussed the Airbus's blade, smooth, shiny, mirror-like wings that will reduce drag and increase efficiency for the sake of decreasing fuel price, etc. Okay, so this concludes manufacturing. In the next discussion, we look at propulsion and engines. Thank you.